Thanks for coming along this morning. My name's Stephen McQuaid. I'm Product Marketing Manager at NXP, responsible for the LPC1500.
I'm Mahesh, working as an application engineer in NXP San Jose. And I have been working on various microcontrollers. One of them is LPC1500, which is one of the microcontroller for motor control applications.
We'd like to cover not just the features of the LPC1500, but Mahesh is going to cover some of the motor control work that he's been doing. So we've got a few demos, as you can see at the front. We have the board spinning with the NXP logo and stuff. So we have that version, and we also have this flywheel both using the permanent magnet synchronous motor, but we also have a BLDC solution kit as well. So the agenda for the presentation: quick introduction from my side. I'll touch on some of the key features on the part that make it specifically good for motor control. Mahesh will go into some more of the technical details, and then I'll cover some of the software and tools and the development platforms that we've got for motor control. Q&A at the end, but if you have any questions as we go through the presentation, just stop us. The more interactive it is, the better it is for us and for you, hopefully. The 1500 has been designed with a feature set in mind that will drive multiple different motors simultaneously. The other thing that's been Mahesh has created as well, we've got a GUI used to tune the motors. So every individual motor has a different resistance, inductance, so some issues there when it comes to tuning the motor. So Mahesh will talk a bit more than that. Some of the customers that I've spoken to are in the consumer space, large home appliance, in the commercial space for HVAC, elevator, escalator control, and the heavy-duty industrial pumps and generators, so the AC induction type motors. But the feature set, because it has, we have 4 state configurable timer PWM blocks on there, so it means it can drive up to 28 PWMs. We have 2 12-channel, 12-bit ADCs on there, so 24 channels in total. So in total, we could, in theory, drive up to 4 motors simultaneously. But that feature set also lends itself to applications like power supplies, similar type control loop, PID control loop, driving FETs for the output voltage and current, and then the ADC channels for remote logging and data acquisition. So this table here is just to try and summarize, the different types of motors out there, the different types of control, whether it's sensored, sensorless, rough different applications, but the key features on the device and the firmware that we provide to help you get to market quicker, and then some of the benefits in your application and the end customer application. So if I take an example of a permanent magnet, so on this type motor here, it does have a QEI sensor in there, so that quadrature encoder, I should say, which hooks directly into our QEI interface on the microcontroller. On the sensor side, so we connect directly to the QEI. But if we're doing sensorless, we use the ADC and the PWMs. So the ADC can measure the currents in 2 of the phases, and you can determine the position, the direction, and the speed of the motor. So the firmware, we have our own engineer-to-engineer website called LPCware. Up there, you'll find an app note explaining the brushless DC. There'll be example code that you can download, so it's all there. The key thing about BLDC is the SCTimer PWM block can drive that on its own, so you can actually shut down the CPU core, and the SCTimer will take care of that. So if power consumption is an issue, then you can shut the core down. So the key benefits of having FOC in the end application is you get low torque ripple, low audio and electromagnetic noise. You get very fine speed control, and obviously it's more efficient in the way it drives the motor. So for large appliances, it's key, these days, having low noise, audio noise is a big concern. So this is the LPC1500. At the heart, you can see there's the Cortex M3, runs up to 72 megahertz. There's up to 256K of flash and up to 36K of RAM. We do have the dedicated on-chip E² PROM, 4K there. But the key thing is the interaction between this SCTimer PWM block, the ADCs, the comparators. So this is all hardwired internally. So to create that control loop, it's very fast, efficient, and the interaction of the comparator and the PWM means if there's an overcurrent condition or an over temperature, then the comparators can shut down the PWMs in a safe way. But in addition, we do have the communication interfaces. We have CAN on there from the industrial side, and we also have USB if there's any in-field updates or for data logging. And we have all the standard serial communication there as well, SPIs, UARTs, I2Cs. Just to give you a reference of where the 1500 sits in the NXP portfolio. So it's pretty much in the middle. So we do all the way from Cortex M0 Plus up to M4s and even dual core M4 and M0s. So it's pretty much in the middle between the 1300 and the 1700, which are existing Cortex M3 parts. So one of the key features as well that I never touched on in the block diagram is the pin matrix or the switch matrix. And what it allows you to do is route any function internal to the part out to any pin on the device. So the benefits of this means that every function can get out, and you can use pretty much every pin on the device. There's a few exceptions like the USB and the I2C that are dedicated pads, but everything else can be routed out. So, for example, you can have your UART going to port 0, 2, or 3, or 4. It's up to you how you wish to program it. So I mentioned the SCTimer PWM block being a specific block dedicated to the timing and the PWM generation. This block's unique to NXP, and what it does is it takes your standard timer, all the input capture, output compare, PWM generation, and you add on a state machine. So the state machine allows you to program various different types of waveforms. It gives you precise edge control over the PWMs. So if you want to create something that's non-standard, then the state machine allows you to do that. We do provide a GUI tool. It's within our own development environment. It's called RedState, and it allows you to program the state machine in the way you specifically want it. But again, these blocks can be, they can either be one 32-bit timer or two 16-bit timers. So again, they're flexible. You can have them on two different time domains, and you can program them up and down. And depending on the states and events, you can create different types of waveforms. So this is an example here where we're within one state, we have two events, and these are two match conditions. So on your first counter match, you toggle the I/O pin, and on the second, you toggle it back. So the counter is continuing to count up, reset, count up again. Second example is if you want to create a center-aligned PWM. So the counter starts counting up, you get your match, but in this case, you start to count back down, and on the second match, you toggle your edge again. So it's within two different states there. So it's pretty flexible, programmable, whatever way you want. You can do pretty much anything you want. Okay, so the ADCs on the device, there's two of them. So the thing to note is it's 2 megasamples per second, so it needs a 50 megahertz clock, but the core itself can run up to 72. So you have various different clock inputs that you can use to drive the ADCs. So it can be the internal oscillator, which runs up to 12 megahertz if you just want to run slow. You've got the system PLL, but obviously there's a limitation to 50 megahertz on the core if you use that. Again, you can use the USB PLL, but you're limited at 48 megahertz. Or you can use the SCT PLL and run it up to 50. And then, you can still have your core running up to 72 megahertz. So the other thing on the flexibility message about the 1500 is the comparators. So there's up to 7 different inputs that you can route to any of the comparators. Can be on either the positive or the negative inputs. Likewise, the temperature sensor is fed into the comparators as well. So again, if there's an error condition, then it can shut down. And there's 3 different propagation delay settings, so depending on power consumption or the speed that you want of the comparator to flip. So that's programmable as well. The quadrature encoder interface, so depending on the number of output pulses and the phase difference between the pulses, you can determine the speed, the direction and the position of the motor. So that's fed directly on the board here, on the motor control board. The sensor is fed right into one of these blocks and then it's fed straight to the 1500. So the other thing is there's an index input as well, so if you want to reset the position of the sensor input, then you can do that. And then each of those pins is selectable, so you can route it out to any pin on the part. Mahesh, I'll let you talk.
So Stephen talked about various peripherals available on this microcontroller for motor control application. One is SCTimer PWM block, which can have up to 28 PWM. 4 sets of independent PWM, minimum 6 each. So in that way you can control up to 4 motors. There is a lot of interconnectivity between peripherals. There is a connectivity between comparator to SCTimer, ADC to SCTimer, and you have ADC also shutting down SCTimer PWM block. And that way you can control various motor like brushless DC motor, PMSM motor, AC induction motor. You can control definitely stepper motor and brushed motor. So you can control all of the motors using LPC1500. One of the example here is LPC1500 controlling 2 motors. One is a PMSM motor and the other one is brushless DC motor. In case of PMSM motor, here it has been shown that we are doing FOC on this motor and it's controlling 2 motors. In case of PMSM motor, the feedback is coming from the QEI. The overcurrent protection is coming from the SCTimer PWM input processing unit, which can take input and shut down the PWM. And this SCTimer PWM IPU block can be controlled by SCTimer PWM block. So it can control when to take the input and when not to take the input. For example, there is an overshoot and you don't want to take the input. In that case, it can control that SCT IPU block. You have ADCs, so there are 2 ADCs. So you can sense 3-phase current. You can sense 2 phases and you can calculate the third one. And you can sample 2 phases simultaneously because there are 2 ADCs. In case of brushless DC motor, you have SCTimer PWM block here and it's generating 6 PWM as same in case of PMSM. But the input is taken from the comparator. It has 4 comparators, so you can take input, you can sense the back EMF from the comparator, and based on that you can control the motor. The other thing is SCTimer PWM block can take the inputs directly from the pin or directly from other peripheral. In that way, you can directly connect Hall sensor to the input of SCTimer PWM block as an event. So there is an event control block in SCTimer PWM which decide which event need to be taken and what to be done at a particular event. And this is a compressor control and the fan control, and the typical example is like AC, air conditioner example. So it's same what I have shown in the previous slide. So what are the key features in LPC1500 to control motor? For example, if you are doing FOC, you want to control ADC using PWM block so that you can sample ADC at a particular time. So there is a synchronization between ADC and PWM block. Each register has corresponding match reload register. So in PWM block you have match registers and you can generate duty cycle. There are corresponding match reload registers, so there is no glitch when you load the new value of PWM. It has dual high speed ADCs, so it has 2 ADCs and each ADC is 2 megasample per second. It has on-chip E2P ROM, so you can store the parameters, any tuning parameter from the motor. It has comparator and ADC, which can directly shut down the PWM block. So for example, in case of ADC, if there is a low threshold and high threshold, it can sense that, and it can shut down the PWM in case of over voltage and under voltage case. And a comparator can be used to shut down PWM, there is overcurrent. The SCTimer, which is an input processing unit for SCTimer PWM block, and you can control this block using SCTimer PWM block, and you decide whether I want a particular input or not, and it will generate a combined abort input. So for example, multiple inputs are coming, and you want to generate a single abort signal. This SCTimer does that. You can go to this white paper link if you want more information on this. So this shows the connectivity between various peripheral in LPC1500. So you can see there is one block, SCTimer PWM block, there is other SCTimer PWM block, another SCTimer PWM, and the last fourth SCTimer PWM block. So there are 4 independent SCTimer PWM blocks, each connected to SCTimer, and all timer blocks are also connected to the comparator output. So for example, if there is a fault condition, you can directly shut down the PWM from the comparator. That input can also go to SCTimer, and there are more inputs coming, so you can combine and shut down the PWM block. This SCTimer PWM can trigger ADC here, and this block can trigger ADC, both of the ADC independently, or can trigger both ADC same time. So in that way, you can decide when you want to sample the signal. So the typical example could be FOC. If you are doing FOC in PMSM motor, and you want to sample one phase and the other phase at same time, you can trigger using SCTimer PWM block. And there are 4 blocks, and there are 2 large and 2 small blocks. The large block has up to 8 PWM each, and the small block has 6 PWM each. You have 28 PWM here, and you can control 4 motors using this LPC1500. This one shows a 6-step control of brushless DC motor. So this simulation shows which phase actually have current at a particular time. So at a time, you need 2 of the transistor, one upper and one cross, to be conducted, so that current will flow in a particular phase. So that way you can have 6 phases, and it's showing the corresponding current here. So this is an example how a BLDC motor is controlled in 6-step mode, and this simulation shows like the stator is an electromagnet, and this rotor is a permanent magnet which has an N and S, and electromagnet you are actually continuously switching the PWM from the motor is rotating. So basically you are generating a moving flux, and you have a rotor which is a permanent magnet, and it will follow the flux. And this is a kind of synchronous motor, so it's continuously moving with the flux. And this one shows the back EMF of the brushless DC motor. This is the current, and this is the back EMF. So back EMF of a brushless DC motor is trapezoidal compared to a PMSM motor which has sinusoidal. So this is the example where one of our board has this, which control a brushless DC motor, and these are the output connected to the BLDC motor, and Hall sensor is directly connected to SCTimer PWM input, so it can generate event, and based on that it can switch to another phases. So there are 6 phases, and input, you are getting input from the Hall sensors. So you have 6 states from the Hall sensors coming, and based on that you are controlling the motor. So, and that is happening directly in the hardware, so there is no software intervention. And this one shows the SCTimer PWM block generating a PWM, and this particular register match 0 is actually generating the period, and match 1 is generating the PWM width. So you have 6 phases, and at a time 2 transistors are conducting, but they are actually in PWM. Here you have PWM, you have PWM, then other one, and that way you have 6 sequences. But each transistor will have a PWM at that time. And how it is done in the SCTimer PWM block. So we have 6 phases, corresponding 6 phases, we have 6 states, and then you have Hall sensor input, which is shown here. So for example, it is a particular state here right now, and Hall sensor input is this. So based on that, it will switch to another state, and because the motor will move, the Hall sensor position will change, so it will move to another. So the event is directly coming to SCTimer PWM block without any software intervention, and it's changing the state continuously from one to other. So this is totally happening in the hardware. So in this case, you can actually put core in the sleep. So this one shows in each phase you have PWM duty cycle, which is generated by the match 0 and match 1. The period is generated by match 0, and match 1 is generating the duty cycle. And that way you are sensing the Hall sensor input and the PWM end, because here you want next stage to be done only after PWM is done at that time, so that there is no cross conduction. And these are shown here as an event. So what is here? The SCTimer PWM block has an event generation block, so which is taking inputs from everywhere, and based on it, it is deciding what to do, and that you can program in the registers. So this is one example where you can directly control motor. Definitely, if you want to do PID, then you need core intervention, but that is a slower loop. This one is the faster one, because every time you want to switch fast. So the state switching is fast, but the PID will be slower loop that you can do in the software. So this one shows the abort condition as well. And you have comparator there, you have ADC input. So whenever there is a fault condition, it will shut down the PWM, because those inputs are directly connected to the SCTimer PWM input. So pins are connected, internally peripherals like ADC is connected, comparator is connected, SCT IPU is connected. So all those peripherals can shut down the PWM when required. Now PMSM motor, this particular presentation is talking about the FOC, how to do FOC on PMSM motor using LPC1500. So LPC1500 has 2 ADCs. It has SCTimer PWM blocks. It has comparator, and they are also interconnected. One of the requirements of FOC is to sample phase current simultaneously. And there are other requirements for safety, like you need a comparator, you need some under voltage, over voltage control to shut down the PWM. All those are available in LPC1500. So now the basic principle of FOC is basically what you want to do is you want to have stator flux perpendicular to the rotor flux, so that you can generate maximum torque. So there is one example here. The rotor is a permanent magnet and stator is an electromagnet. So you are actually energizing stator in such a way that the flux of the stator is perpendicular to rotor. So in that case, it will generate maximum torque. Torque means the rotating force, right? There is a condition where the N is pulling S or the S is pulling N here. So that one is the happy state of the motor. The motor is happy there, but it's not generating any torque. So the basic principle of FOC is to make stator flux perpendicular to the rotor flux. and that can be done by sensing current. So you cannot sense flux directly. So what you have is the current. You can sense the current. So you can sense the phase current A and phase current B. And then you can have a arbitrary vector where you can say that, okay, this particular moment the current is, the flux is actually in this direction, and you can have the right angle and quadrature. You can have two components of the flux, and then you want to put one of the quadrature, one maximum, and the parallel one 0. So basically any flux coming parallel to this one you want to be 0, and so parallel to rotor you want to make 0, and perpendicular you want to make maximum. So that is the principle of the FOC. And using LPC1500, you can sense the current, like for phase A current or phase EV current, simultaneously using ADC 0 and ADC 1. And from here, you know the current, then you can have Clark and Park transformation. From there, you can have a space vector, and you can calculate the PWM values, and you can have SCTimer PWM programmed with the PWM values, and then you can generate PWM. So ADC 0 you can use to measure the phase A current, and ADC 1 you can use to measure the phase B current. And based on that, you can control the quadrature current and quadrature flux and the direct flux. You want to always make the direct flux 0 and the quadrature flux maximum to produce maximum torque, because you have mu b sine theta from where you can generate the maximum torque. I have a motor here, and this one is using FOC control, and you can see that this motor is rotating at a particular speed. We have a set speed here which is 261, and the RPM which is the actual speed which is coming from the motor. So you have a QI sensor here, the mode is QEI, and the RPM right now it's 263, it's actually varying little, and the set speed is here. You can change the speed. So the motor will rotate faster. Set speed and the actual speed, they are almost same here. You can tune the motor using Kp, Kb, Kg and Tg value changes. The inner loop, which is the direct flux and the quadrature flux control, is actually done with all these 6 parameters, 3 for Q and 3 for D. This is the rotating vector, and this one is the constant vector, which is required in case of the FOC. So what is happening? Your motor is rotating, your flux is also rotating. So in that way, the calculations are very difficult when the motor goes fast. So what you want to do is you want to be in rotor reference plane, and then you want to calculate the PID loop. So this particular GUI has some feature. One of them is oscilloscope feature, and it will show you the auto range. You can change auto range to a particular value. So you have read a set speed and you have a actual speed, which is the speed the motor is running. I can change speed from here. So you see the blue is the set speed and the red is the actual speed, which is following the set speed. So this is one of the feature of this GUI. You can tune various parameters from here. You can turn off motor. So now I turn off motor and it's off. it turned on. There is data logger as well. You can log the data. So here tool will show all these things, the scope and the data logger, and you can also save the file into your PC, the parameter file, and then you can use them later. You can change the motor speed. You can also tune the motor using the KPKI TZ. This one is tuned for this particular load. So you can use this GUI to tune for your load. In summary, we can say that in LPC1500 we have 2 ADCs and we have SCTimer PWM block. And there is a connectivity between SCTimer PWM block which can be used to control a BLDC motor, PMSM motor, or any induction motor, and definitely the brush DC motor and the stepper motor. You can control up to 4 BLDC motor independently without any software intervention, because everything is happening in the hardware, in the state machine. And you need software intervention only if you are using some PID calculations in your application. That's it from my side. Steve will talk about more.
Okay, thanks Mahesh. Okay, so another quick section just on tools and software that's available. So it's not all about just getting the silicon. We want to try and help to make things easy when you're developing. So we've got some software wrapped around about it. So as I mentioned before, we have our engineer-to-engineer site, LPCware. And on there we do have LPC Open that you can download. And that's sort of initialization drivers, low-level drivers support there. So it's a standard platform. We develop all of our code internally based on the LPC Open platform. It means that we have lots of reuse, and I'm sure that's important with all your projects as well. On top of that, we do have board support packages. So we have the Espresso board. We also have a Kyle board that we use as well. So those board support packages are available. On top of that, we have middleware. So we have drivers, stacks for USB and for CAN, which is on this part. And then we do have our own IDE, the LPC Espresso. We support Embed for prototyping, and then we do work with Kyle IER as third parties. But the key thing to point out on this is this part is 256K flash. So the tools, you get a download limit of 256K, so basically the tools are free. So it's $30 is the charge of this board, but everybody will get a free board anyway, so development is free basically for you on this. I mean, if you do need the full support package, then the Pro Edition it's only less than $500, so it's pretty cheap when you look at it as a whole development environment. We do have 2 solution boards, solution packages. So this one, the permanent magnet, and the brushless DC version, which we've got here. So we do have both those solutions. The base board is the same. It has the Espresso that plugs into the motor drive. The thing to point out is the drive itself, it can only drive up to 24 watts. So obviously if your application's bigger than that, then the drive circuitry would have to change. Same there. So Espresso board, the key thing about this is it's a new version of this board. So what you do get on here is a debugger as well. So so you can debug the target, the 1500, or if you've got any other device that you want to debug, you can use this as well. So there's no need for a hardware debugger. It does support Arduino. So if you're doing any other development, you want to plug in some other cards, then you can plug in the Arduino. It's also got PMod for the embed. So it's pretty flexible little board. So yeah, so the key places for information if you're looking for anything else on the 1500, NXP.com and LPCware.com is the 2 places to go. And then just to finish up, a quick summary. So the 1500, it can drive various different types of motors, brushless DC, permanent magnet, AC induction, drive multiple motors at the one time, so hopefully saving you system cost in your own design. Sensored and sensorless control, so we've got the QEI for sensored and the ADCs for the sensorless. We've got the GUI, we've got the demo code, we've got the FOC. What I should mention is that piece of code, that PID loop, is only something like 11K of flash, so it'll run in any of the versions of the 1500, and it runs in about 40 microseconds. The key thing to remember is the interconnection between the SCTimer PWM, the ADC, and the comparators, so creating that tight control loop. And then if you look at the pricing compared to the competition, I think you'll find that we're pretty competitive against the competition, so it's a pretty cost-effective solution when you look at it. So thanks for listening. Thanks for coming, guys. Thank you.
Thank you.
Thanks.